As people have had just so many questions, I'm just going to go straight ahead and fire them at you. So I hope that's okay. So first up, something I think a couple of people have mentioned, Jim and Shearer both asked sort of similar questions, which is, did the universe violate the speed of light during the inflation? So if the space-time can grow faster than the speed of light, does that contradict the fact that things can't travel, or is it because it doesn't contain information? Is that the key thing?
No. It's absolutely consistent. Within space-time, you cannot be faster than light. No, but if the space-time itself grows, it has not this limit.
But does it have any limits theoretically, or could it theoretically?
No, theoretically no. No, depends on the density of energy it has inside. It could expand at any speed. And actually, there are several pictures of the first instant of the inflation, which assumes different speed.
Interesting. Another question here from Anand. This is something that I hadn't really thought about. What's the current estimate for the margin of error in the age of the universe? I sort of know 13 and a bit billion years is sort of what I think, but I don't know how precisely do we know that? Is it sort of plus or minus a billion years or plus or minus 1 year?
No. We are. I think it's 0.2%. The actual.
Wow.
If I'm not wrong, but if you pay 0.2% on 13.8 million is quite sizable, but it's very precise. Depends on this. Basically, this information comes from Planck, the most Planck satellite. The picture that I show of the cosmic microwave background, the precision by which you are able to appreciate these small anisotropies translate in precision in the age of the universe.
Interesting.
So it will be improved. I'm pretty sure this will be improved with the next missions.
Another interesting question, which is this idea of a zero energy universe. So Adam asks, if the universe has net zero energy, then why do we need an initial singularity of infinite mass?
No, but in fact, this is not anymore. I mean, this was in some sense, there is still a prejudice of the traditional Big Bang theory, in which for many years people were thinking that there is something in which you have a huge amount of energy and mass, infinite amount of energy and mass, and this creates the mechanism of the Big Bang. While within the cosmic inflation, there is no need of energy. So it's an incredible nice situation, having discovered that you can mix together mass energy and space-time, and one has positive energy, the other one has negative energy, you put them together is zero. Now, this was the thing that was fascinating for Stephen Hawking. I had the privilege of being a friend of him for the last period of his life. It seems to be the simplest solution to an incredibly complex problem. Now we can somehow answer the question.
Sorry about that, everyone. So we'll just carry on. One of the things that Les mentioned is, where does antimatter fit into this Genesis story? So obviously there must have been a time when we ended up with matter and not antimatter, and so how does that fit into the?
Very good question. Actually, in the book. Today we don't know why the current universe is dominated by matter, because every, let's say, theory hints that there was initially a complete symmetry between matter and antimatter. And now there are two possibilities that we are investigating. One possibility is that during the evolution, antimatter, for a certain amount of, with a certain amount of probability, prefer to decay in matter. A tiny preference in 13.8 billion years would have resulted in prevalence of matter to antimatter. Basically, if there is a small preference for antimatter to decay in matter and not in antimatter, sooner or later the entire universe would have been in matter. So we are looking for some anomalies, some difference in the decay of antiparticles, We have seen some of this small preference, but not large enough to describe the current situation. Another possibility is there are anti-galaxies somewhere. We have not seen yet them. So people are exploring corners of the cosmos in looking for hints of large quantities of antimatter. No way so far. Third possibility, the Higgs boson itself. At the moment in which the Higgs boson couples to elementary particles, there could be a slight preference for matter with respect to antimatter. So if the Higgs boson would have preferred to couple to matter, then this would have explained the current dominance of matter. So far, we are not been able to measure the properties of the Higgs boson to such a level of precision to be able to say this is the right solution. So we are exploring different paths. For the moment, we have no answer.
Oh, excellent. Well, we know what the answer is in terms of we have matter and we don't have matter. So there must be something that, you know what I mean? Like it's something we must know. An interesting, Amy asked this question, which sounds kind of simple, but then I was thinking, maybe that could be possible. So Amy says, is it possible there may be more than one Higgs boson? So I know, for example, there's 3 different types of neutrinos, and many other particles come in different sort of, I was going to say flavors, but then that actually has a specific meaning, so I shouldn't have said that. But you know what I mean? There are different types of other particles. So could there be a Higgs boson with twice the energy, for example?
It is something that we consider, and we are looking for, let's say, other members of a possible family. No, there are theories hinting of an entire family of Higgs boson. The one is very similar to the standard model Higgs boson, but then there are others that would imply immediately that the standard model is not correct. Remember that now we have basically discovered all the particles foreseen for the standard model. But the standard model, as we are discussing just now, is not able to explain why antimatter prevails, or why there is dark matter in the universe, or dark energy. So there should be something else. No? We are looking very carefully in the LHC collisions and also in astroparticle collisions to look for other scalar particles of different masses. If we find just one, that would be a major discovery, because one particle which is not member of the standard model means that the standard model should be changed with a new theory, more complete theory, for which the standard model will become a low energy theory. So the time in which we be able at CERN or in a deep underground or in a satellite experiment to come out with a new scalar, something connected to the Higgs boson, but not exactly the one that we have captured at CERN, that will be a fantastic moment.
And actually, you hinted at my next question in your answer there. So Jim and Ian are both asking, where do dark matter and dark energy fit into this sort of picture of the early universe? I mean, were they sort of present immediately after the Big Bang, or do we think they might have emerged at a later point?
Yeah, the dark energy, yes. Dark matter, yes. Dark energy is something that we think it has appeared recently, quotation mark, let's say 6 or 7 billion years ago. No, so the expansion of the universe has changed. Let's say the rate, and this accelerated expansion we call effect of dark energy. We don't know exactly what it is. Could be a sort of anti-gravity, or could be a property of the vacuum, or could be something connected with the inflation. Maybe the initial inflation has rested for a while and then started moving ahead. We have a lot of that. We don't know absolutely what is the origin of dark energy. Dark matter is present in the early universe. We think it is present in the early universe. We have also, people have also produced maps of the web of dark matter. Around the nodes in this web, we have the formation of galaxies and stars and galaxies. So it has played an important role. Again, here we have evidence that it is present today. It was present at the very beginning. but we have no idea what are the components, what are the particle component dark matter. So the embarrassment in this area is huge because we have not yet discovered nothing that could explain this element, which accounts for 27% of the mass of the universe, has played an important role, is a large fraction of the universe, and we are really embarrassed in say we don't know at all what is made of.
Just going back to the antimatter point, Lawrence asks an interesting point. If I'm just looking at my telescope, like that wonderful deep field image you showed near the start, and looking at one of many, many millions of galaxies, how would I know if it's an anti-galaxy? How would we actually identify it? If it's so far away from everything that the anti-particles or the anti-atoms aren't interacting with anything, how would I know that the light coming from this is coming from an anti-galaxy and not a regular one?
It's a very good question. You should what you need to do, you should take a look to some interaction of this world. Let's say, suppose that you discover a galaxy or a cluster of galaxies. You have to take a look to their properties, and in particular the interaction. There will be different interactions, and there will be sign that you can collect of, for example, sign of annihilation. If there are large quantities of antimatter around somewhere, you should have a flux of photons, for example, coming from the annihilation of matter-antimatter. You should have sign of the presence of antimatter in terms of different interaction with other galaxies or other cluster of galaxies, or anomalous production of radiation, or presence of positrons is another sign of possible hint of presence of antimatter. And those signals are actively searched by many experiments.
Gavin asks, what do you think about Roger Penrose's ideas about the repeating universes so that you can see influence of previous universes in the cosmic microwave background?
This is a very good question, because there is still a long debate among scientists. By the way, if one goes back in history, the stoical view of the world was that every 60,000 years there will be another universe with another Plato, another Aristoteles. Now this is an old story, the one in which one imagine a cyclical universe. And actually it was quite popular also in the 60s, this idea of having our universe expanding up to a certain moment, and then gravity prevailing, the universe bouncing back to a big crunch, and then originating another big bang, a sort of a continuous cycle of universes, basically. This perspective today is not considered realistic, because we see basically dark energy. The fact that we have the galaxies and space-time basically is accelerating, so the expansion is accelerating, means that it's very unlikely that we come back. Nevertheless, it would be interesting to take a look to the properties of the cosmic microwave background, because we could find anomalies that cannot be explained by fluctuations. And this could be the origin of a speculation that might be very interesting. Are those footprints, for example, footprints of another universe? This could be also the case. Or some remains of a previous story. I don't know. All this could be taken seriously the moment in which we have evidence that structures that are present experimentally in the cosmic microwave background cannot be explained with the standard, let's say, explanations.
Alexandra asks an interesting question. How does something that has non-uniformly spread matter, like the universe, it's kind of clumpy and non-uniform, but how come its expansion is uniform?
No, but the uniformity is quite, the actual universe is quite homogeneous uniform. There is not, so if you take a look also distribution of matter, I was alluding the time in which I was describing the slide with the full universe, is quite repetitive. So there is quite some uniformity in and actually the extreme uniformity of the temperature of the cosmic microwave background is one of the most important, let's say, supporting elements of the theory of the inflation, no? Because there is no way for a universe to communicate, to this large distance and to stay at the same. Imagine for a moment that the photons of the cosmic microwave background have a phone and call each other. No, be careful. There are the scientists of planet Earth looking at us. No, so we have to organize to tune not the clocks like in the movies, but the temperature such that at the extreme of the universe we should arrive to planet Earth with the same temperature. No. So the fact that it is so uniform is really a sign that there has been an expansion from a very tiny object. No? Is a convincing supportive element of this.
So Fabio, who sounds like a fellow Italian by the name, asks, could you say a few words in your opinion on the multiverse predicted by string theorists? String theory, and how to infer evidence about it. We've had a few talks. For those watching, we've got some great talks on our YouTube channel about this from Sean Carroll, who has a very particular view of the multiverse, and Jim Baggett, who has a very different view of the multiverse. So I wonder where you stand on the kind of many worlds and the multiverse theory.
Yeah, it's a very good question, because basically, if the mechanism is the one that I was describing, is basically, we are here by chance, by quantum fluctuation of vacuum, extraction of inflaton, and that's it. And there is no reason why this mechanism shouldn't be happening continuously, basically. So one has to imagine a mechanism, an inflection, a cosmic inflation that is not happening once, but could happen several times. Makes no sense because the time is inside our universe. But anyway, just to understand each other. And so, personally, I'm very attracted by the idea of the multiverse. Although it is a conjecture, clearly we have no evidence that this is the case. People are looking for experimental tests of this conjecture. And I would be delighted to have some evidence of this. But let's stay on the purely logical level. Logically, it makes sense. Makes sense that we should basically, let's put this way. For a few thousand years, we have thought we were at the center of the universe. And then Galileo came, and then later Hubble, and then we discovered not only that we are not at the center of the solar system, but also that our solar system is a small peripheral system in a galaxy. Our galaxy is one over 100 billion galaxies, but still we have the universe. In the world, we have the sort of unique role for us. The moment in which we will have the experimental test that there are at least the possibility that there are many more other universes with different conditions, with different constants, with different evolutions, that makes absolutely sense. We would have lost probably the last sign of arrogance. So I look at this also with some sympathy.
So Rafi asks a question, do you think that it will be the particle accelerators that will be the key to finding out what dark matter and dark energy are, or do you think it's more likely to come from astronomical observations or satellites or
I don't know. Yeah, I don't know. I hope that we will have the possibility to discover something that will display. But again, for the moment, basically the two things are complementary. Basically, we are able to explore up to a certain amount of energy, because beyond the energy of LHC, we cannot explore. So nobody has decided that the dark matter particles have a mass which is within our reach. Remember, energy equal mass. So if you don't have enough energy to produce the right mass, you will never see dark matter particles at LHC. So we might be unlucky, and experiments in the satellites or underground that have not this limit, have limits in sensitivity, they could be able to see objects which are, let's say, more exotic. So we don't know, and the two things should be pursued in parallel, because in some sense they are complementary.
And while we're on the subject of dark matter, someone in the chat mentioned MOND theory, MOND, which stands for modified Newtonian dynamics. And from what I know, it's a kind of alternative to dark matter. I just wanted to know, do you think that's a likely candidate for a theory, or do you think dark matter is actually a much better explanation?
I know quite. I read some articles on the theory. And I think is something to be investigated. No, we have to be serious. We shouldn't. I think there is not an obvious flaw. No, the theory could be taken seriously into account. In this particular case, I think the measurements are astronomical measurements. So we have no possibility as accelerator scientists or particle scientists to test this modification of the gravitation, basically. But there are astronomical phenomena that could be measured with high precision. We should probably produce new equipment, new infrastructures to be able to access some of the precision that would allow us to say yes or not to this conjecture.
So I've been trying to save this question to the end, but the people in the chat have been demanding it. So it's exactly what we were talking about earlier on, which is the announcement from LHCb, one of the experiments at the Large Hadron Collider earlier this week, about I'm going to get this wrong now. Can you? I'll let you say it. Can you just explain a littleit about what the discovery was or the announcement was this week, and how you think this might affect some of the things you've been talking about potentially?
Yeah, it's a very nice measurements that was announced in the winter conference that we have that happens during the beginning of March by the LHCb experiment. That is the one of the 4 experiments, is specialized on B-physics, on the production and decay of this heavy quark, which could be a good laboratory to test, stress some of the standard model predictions. So I was telling you before that today we have a picture that and we are very proud of the standard model, but we know that the standard model will not work forever. In particular, is not able to explain some of the things that we are discussing before, dark matter, dark energy, asymmetry, matter, antimatter, and many others. So we are looking for unambiguous hints that there is something new, no, beyond the standard model. And one way of doing it is to discover directly new particles. That would be fantastic. But another way, which is less, I would say, exciting, but for general public, but for us is similarly exciting, is to perform precision measurements and detect anomalies. No? If we detect an anomalies, that means that this particle interacts with something that we have not foreseen, interacts with the new particle, maybe very heavy, and we see the effect of this interaction is in indirect measurements of the presence of heavy particles beyond the standard model. And this is exactly what we are trying to do, and LHCb did succeed in doing, looking at decays of this particular state of matter containing a B quark and an S quark. They discover the theory predicts that the same number of decays should go in electrons, in muons, and in tau, the 3 leptons. The 3 families, we are democratic. Nature is democratic. Should give the same amount of vaccines. We are in this period in which we are discussing the vaccines in different countries. The same amount of shipment should go in electrons, in muons, etc. And they've discovered that this is not the case. So there is a what they call a lepton flavor violation. So a small asymmetry. Again, the difference is 3.1 sigma. That means that could be still a fluctuations, an underestimation of the systematic errors, could be many reasons. But could be also the first hint that something is happening. So what is happening now is that there are other experiments like CMS, like Atlas and others that will try to perform similar measurements or measurements in other channels. And then in a few months, or let's say in a year, if we start collecting evidence in other channels or in the same channels with other experiments, then the possibility that this could be a fluctuation will become smaller and smaller. And then if this would be the case, so we should be patient, I would say a year, we might come up with something that is consistent with the fact that we are seeing new physics. It's too early for the moment, but keep an eye.
Wow, that's absolutely fascinating, and I think it just goes to show lots of the comments and lots of the news stories. People are still, even after the Higgs boson, I think there's still huge public interest in the work of CERN, and obviously the discoveries you're making every day. Because just the questions that I've had just on that one thing alone have just been have been numerous. So yeah, I think it's a fantastic. It just blows my mind every time I think about CERN and the engineering, the science, the brain power that's gone into it already. And just like you were hinting at, these discoveries that are just tantalizingly there, and we still have a lot more work to do to find out. So thank you so much for that brilliant presentation and for explaining some of the fantastic work that you do.
Thank you, Martin. Thanks, everybody.